So great. Yeah, nice for everyone who's here in the room, even such as just virtually. I'm Nils, working for Cohere as Director of Machine Learning. We're building foundational models. One big application is semantic search. And also here's Etienne, who's like not living too far away from where I'm living in Germany.
Which we just realized during the planning session for this webinar. Yeah, we could have almost had it like in person, at least the two of us.
Yeah, in person.
Yeah, but yeah. Hi, also from my side, one of the co-founders of Weaviate. So here for all your vector database questions today. Great.
So yeah, just to give like a short overview, what is Cohere? We're training foundational models and expose them as a service. One big use case is generate. All the people probably have seen the media hype from ChatGPT and GPT-4 in the past 6 months. So basically you give like a prompt in and then you generate the output based on the prompt. So really popular with students to do their writing assignments and use the help of AI to do it. What I always find interesting and which I'm in charge of at Cohere is text understanding. So this is especially interesting for enterprise use cases. In an enterprise setting, you have like a lot of data. You have like millions of customer voices, how they like your product, how you can improve as a company. So you want to be able to analyze the data. You want to be able to search on it. You want to be able to classify. So for example, what product do they talk about? What features do they like, dislike? And also content recommendation is a big focus. For example, on a news website, which other news articles are interesting? If you do like some reading, you want to do like a deep dive on some scientific topic, what other papers can complement your work? And that's what I'm working on. Here, embeddings is a foundational technology, so it's a bit harder to grasp, but we will try to capture it. And as soon as you hear the word embeddings or vectors, there's also the vector database, which really helps to manage these vectors, help to orient it in the vector representation. And yeah, you can get, if you understand the technology, get amazing results in the text understanding space. So big focus is search. And sadly, search, it's frustrating. So there's like hardly any good search functions so far, besides like Google and Bing. If you go on one of the most popular websites on the world, Wikipedia, and you hit this search bar and you type in like a really simple search question, like what's the capital of the United States? It's not too complex. I mean, maybe you're a student, you want to do like have some writing assignment and you want to need to know like what's the capital of the United States. You see the first result about capital punishment in the US, and then also the second and third and all the other results on the first page, the first 20 results are completely useless. So no results talks about Washington, D.C. and presents the relevant information. And this is like for one of the most popular websites on the internet, which is like visited by 100 million of people. And the big issue is that Wikipedia and like most other search functions run on lexical search. So lexical search, it's like the string F find in your browser or in your PDF document finds like documents that contain these words. So it finds where this document matches the search query because it contains the word capital, United States, and also like the and is. And it contains these words quite often. So lexical search thinks this is a really good document. It should be shown to you, but it's not really understanding what do you want? What do you want to see as a search function, as a search result? So there's like no understanding of the meaning of your search query and the document. But luckily, there has been like tremendous progress in the past 5 years to make it really better. And now it's really possible to get like an amazingly good search function with like little effort. And here, text understanding, embeddings, and vector databases play like a critical role. So if you switch it to semantic search and phrase the same query, what's the capital of the United States? First result is on Washington, D.C. And yeah, you say, okay, that's the right result. The model understands how capital of the United States is connected to Washington, D.C. understands the sequence of the words and can show you the results. So how does semantic search work? So what you do is you take a collection of documents, for example, all the paragraphs on Wikipedia, you pass it to a large language model, and this language model gives you a vector space. So every document is represented in this vector space. Here's like a two-dimensional vector space, but in reality, you would use like a vector space, which is like higher dimensional, like 700 dimensions, 1,000 dimensions. And what's special about this vector space is that it captures the meaning of your documents. So the model was trained such that similar content is like closed in the vector space. And this allows you to search. So you take your documents, you put it in the vector space, you store it in Weaviate, and then at query time, you take the query, what's the capital of the United States? You also put it through this embedding model, this vector model. You get like the vector in the vector space. And then you ask your vector database, you ask Weaviate, which documents are close? And because the vector space understands the meaning, so understands when I search for what's the capital of the United States, understands that I'm looking for Washington, D.C., knows I have to show you the Washington, D.C. result. And this makes like, the search results a lot better. And also we see like continuously improvement on these embedding models, how they create like nicer vector spaces. So you constantly see like better search results. How does it do this? So how does semantic search give you better search results? First, it understands the meaning of text. So it really looks into the text, looks into your query, tries to understand what you do, and really tries to match it to the document, and does the document answer your question? And so what we also saw in search over the time, the behavior of users changed. So for a really long time, Google just worked in a keyword search setting. So people learned to know how to use Google, how to phrase the question as keywords. But now you see that people more put like full question, like what's the capital of the United States? So instead of searching for Washington, D.C., they put in like the full question and expect an answer. And also especially with like younger people that are like less exposed to like the old way of keyword search, expect more and more that you can phrase your question, sometimes put like really complex, complicated questions in the search bar and expect a good search response, because basically on Google you have it, so they also expect it from your products. Semantic search can understand synonyms and acronyms. So in lexical search, niches like when I search what's the capital of the US and my document talks about United States, lexical search cannot understand that US, USA, and United States is connected. So traditionally what people do with Elasticsearch and lexical search is like get a long list of synonyms, and each time I see the word USA, I add to my index, lexical search index, also the word US and United States. But that's not really like scalable and pleasant to maintain and extend the synonym list. Semantic search works with spelling variations. Let's say your document collection uses American English and it has the word color, but there's like someone from UK using British English searching for color. With lexical search does not know that these two, it's the same. So it will not find like any results, which is like really unpleasant. Spelling mistakes. So what's the correct spelling of Hawaii? So this is like a challenge for people. Do I spell Hawaii like this or this or this? Again, with lexical search, only the correct spelling is found and you have to type in the correct spelling. And also semantic search can understand the word order, and especially for more complex queries, the word order plays an extremely critical role. Other big use case is content recommendation. We know it from Netflix or YouTube. You go on YouTube, you see some video, and then it recommends you other videos you might enjoy. This is in the back, like also like semantic search. So every video is an embedding, and then you say, okay, the video you just watched is an embedding. All the other videos are also in the vector space. So you do like the same search operation in your Weaviate database, and then you find the similar results. Also on content, text content, if you read like a news article, you can take the news article as a query and then find other news article that's interesting. And finally, what's super cool about semantic search, it works amazingly in a multilingual and multimodal setting. So multimodal means text to image. As a search engineer, multilingual lexical search is one of the most painful experience I went through. In English, you can tokenize on white spaces. So you look at the text, and each time there's a space, there's like a boundary between the words. And then you split on the words and you put it into like an index. And then if you search for United States, you find like all documents that contain the word United and all documents that contain the word States. And then you do like a set comparison and say, okay, which documents contain both words? On English, this works, but if you have to deploy such a system for like, let's say, Chinese Wikipedia or Japanese Wikipedia, there's sadly no white spaces in Chinese Japanese. There are like many different ways how you can tokenize Japanese, more on like a semantic level, more on a syntax level, but everything is like really painful. Then also what you often do in lexical search, you have like some stemmer, which is like removing the suffix of a word like cat and cats. You want to have both as the same word. You're removing stop words like is, the, a. And this is like all language specific. So if you do this in English, it doesn't work in Chinese. And then often you add like components to your lexical search, like spelling corrections, synonyms. Obviously, if you do spelling correction and synonyms for English, it doesn't work for Chinese. So you have to redo it. And as there are like several hundreds, thousands of languages, it's really painful to build like a lexical search function for Wikipedia, because it's not like one setup, but at the end you have like, I don't know, 300 different setups for the 300 different Wikipedias, which you need to maintain, scale, and improve. So no search engineer wants to do this. But the nice thing about semantic search, about these vector spaces, is that a vector space doesn't care about the language. So it's not grounded in the words. So it's not really say, okay, here I have the one word, here I have the other word, but it's like grounded in the meaning. And the meaning of word is like independent of the language. So if I have like the word sentence like 2 dogs in the snow, or like the German translations by Hunde im Schnee, or the Spanish version of the sentence, or the Chinese version of the sentence, it doesn't matter. It can still be projected to the same spot in the vector space. And then you're able to search in your Weaviate database in this. So if you do like multimodal search, you put this in a vector space, you put all the images also in the vector space, and then you're able to find this image. No text description needed, no translated description needed. You're just able to find it like from the content itself, and it also works on a text level. It makes it a lot easier to deploy multilingual semantic search. So before on Wikipedia, you had like these 300 independent systems, which you need to maintain, test, scale, develop. Now it's like a single system. So you take your documents, you pass it through the large language model. The model gives you an embedding, you put it into your Weaviate vector database, and you're good to go. And it works for English, it works for German, it works for Chinese. Any improvement you do on this embedding approach is beneficial for all the languages. So it's no longer, let's improve like English search, and then maybe if we focus on like Spanish search. But we focus on search and make search better for any language and any customer. Getting started is kind of easy. You go to the Cohere website, you sign up, you get an API key, you install our Python SDK, or if you're on JavaScript or on Go, the respective SDK, you specify your documents, and then you do like a one call where you say, this is my documents, this is the embedding model here, like a multilingual embedding model. And then you get the embeddings back and you hand it over to Weaviate to get it indexed. Or as Etienne will present, it's also easier, can be easier, much easier than that, by using the plugin in Weaviate, where you just paste your API key into Weaviate, and then everything is done by Weaviate for you. Some comparisons, so there's also OpenAI in terms of, which is also like an embedding provider. There are like different open source models. What differentiates Cohere here is one, the capabilities of the model. So here's like a recent benchmark from the University of Waterloo, like semantic search on Wikipedia. We look at like the top 3 hits, if there's like a relevant hit. What we see, the multilingual model is like on par to the OpenAI model. We have like an interesting model upcoming, a new English model and a new re-rank model that gives like another big boost in performance, especially for really complex queries. Supported languages, we're supporting out of the box 100 languages, and we really tuned it for like a production setting. So you're able to deploy it in your own cloud. This gives you like an extremely good latency, and also it's really suitable for sensitive data. So if you have like some personal information, or in Europe, you're bounded to a GDPR, you don't want to send it over the internet to some US data center where it's really unclear and where there's also like some history of like data leakage, but you really want to have it in your own cloud. So we really focus on these enterprise settings to really enable the search cases here. Great, that's so much from my side. Handing over to you, Etienne.
Perfect, thank you. Let me see if we can smoothly share the screen. Wow, I think that actually worked. Yeah, so Weaviate is the other part of that equation. Weaviate is an open source vector database. That means basically, as Nils just said, once you have those embeddings, once the Cohere API created those embeddings, you can import them into Weaviate, and Weaviate is both your storage, but also your retrieval engine. So for any kind of query, Weaviate would process this and it would do that at any kind of scale and do it efficiently at that scale as well. With Weaviate, the main benefits, and there's a much longer list of features, but I try to narrow this down to the things that I think are relevant here. Weaviate always has this kind of end-to-end approach. So it tries to make it easy for you to give you the full experience. So for example, we had a question in the chat come up before already that I saw that while Nils was talking about, where is the original text stored? Is that also stored? And yes, it is. So Weaviate stores the entire data object, and we'll show you in a second, because we also have a demo coming up of what that means and why that is beneficial. But from a sort of high level perspective, it means you don't need a separate key value store anymore. Like if you have a separate vector index, and then you would only get the vector ID back, and now you actually have to retrieve your object from a different store, then you'd have 2 systems again. But Weaviate eliminates that kind of need. It just has everything in one tool, basically, or in one application. Weaviate gives you low latency retrieval. So if you do 5 or 10 or 100 embeddings, that doesn't matter. But if you go into the millions or tens of millions, then that does matter. It gives you support for complex filters. So if you're moving from, for example, the SQL space, where you're very familiar with where clauses that you can combine arbitrarily, that is a great feature, and that is something you want to keep just because you do semantic search now, and Weaviate gives you that part. And then, of course, also the whole production aspect of it. How do I deploy this? How I distribute this? Can I make this highly available? Can I scale this? These are all the things that you get with Weaviate out of the box to run reliably in production. This is an example of Weaviate's GraphQL API. So this is a search on, well, I'm a big wine geek, so my examples, they're always either about food or wine. So this one is about wine. And the query here on the left side, this is a get query on the class wine. So this is a user-defined class that was called wine, and then near text. And now here, all the magic basically has already happened. So the user puts in authentic Italian wine. And as you can see on the right side, it matched a article or a snippet here that matches Barolo. I think it doesn't even contain the word Italy. I'm not sure if it contains the word wine, but basically it was a good match. Why? Because this Cohere embedding We created a Cohere embedding for the text at import time, and we just created a Cohere embedding. I'm going to show that live in a second, or something similar live in a second as well, at query time. So this is, as Nils just mentioned, this is the integration between the Cohere API and Weaviate. In Weaviate, we have this what we call module system that allows you to plug in different parts. And in this case, we call it text-to-vec Cohere. A plugin or module is plugged in. And that gives you sort of, again, this end-to-end experience. You just type in text. It looks exactly like a text search engine, but in the background, this actually did a semantic search. And you see the object is returned as well, which means to the user, of course, you don't want to serve them vectors. Yes, you want to use vectors under the hood, but to the user, you want to serve them a modality that they understand, which is text or images or something like that. So you get the whole object back, including the text. I just mentioned that this is fast under the hood. So if you do this at a small scale, you can brute force this. So brute force would essentially just mean you compare any vector that you have with your query vector, which does not scale at all because it makes it sort of linear, or depending on the use case you have, even exponential. However, there are ways to do that much faster and much cheaper. And this is called ANN, or approximate nearest neighbor search. And as always in engineering, it's always a trade-off. There is also such a trade-off with ANN, where the trade-off is between latency and accuracy. So typically, and if you find good parameters, then the accuracy that you have to give up is very small. So for example, it's very common to run with 99-point-something% recall. And we actually have benchmarks on the Weaviate website where you can see that trade-off visualized. But there are also cases that say, like, for me, it's okay to have 95% recall if that gets my cost down, for example. So it's always sort of power to the user, choose what is right for you. And we use an index that's called HNSW, which is a graph-based index. So that is why there is this beautiful graph illustration on the right side, which is a small world graph. So the idea is basically that by the people you know, and if you go through sort of along those hops, it's very easy to meet someone at the complete other end of the world just because you know someone who knows someone who knows someone, and all of a sudden you're on a different continent. And this is the kind of principle in that proximity graph that HNSW uses as well, just with vector distances. So basically, a vector is connected to another vector, is connected to another vector, and then you can efficiently traverse that, or Weaviate does that in the background, basically, to give you the right results. I mentioned before also that Weaviate has a powerful filter API. So by default, every text, every property, every number, anything that you throw at Weaviate will index it by default. You can, of course, turn indexing off for specific things, like if you have a really massive use case and there are things that you know that you never query them, you can turn them off. But by default, everything is indexed. So really, you can get started with Weaviate, just import a data object, and you know that you'll be able to filter on anything that was in there. This is possible even with multiple levels of nesting or chaining. So you could say, give me all the wines that cost more than $10, but less than $30, that are produced at least 10 years ago, and exclude Chardonnay, for example. So it gives you the ability to do these kind of filters, and still, of course, not just filter, because I mean, like if you just want to filter, you don't need a vector search engine or a vector database, but combine that filter with the actual semantic query. So you could have all these kind of restrictions about the wines that are allowed or disallowed, and then search maybe for a review. And you could go for like refreshing mineralic wines or something like that. And then the Cohere embeddings would be used in the background to do a match, even if there's no lexical match. Weaviate uses a unique way to do filtering. So we have something that's called a roaring bitmap index, which is a relatively, it's unique in the vector database space, and it's in general a relatively new kind of technology that makes filtering super fast, and also allows for the combinations of filters. They're essentially just bit merging operations under the hood, which are super fast. So that gives you the ability, for example, to match hundreds of millions of objects in single-digit milliseconds. So to retrieve that kind of bitmap and then do something with it. So that was the point when we introduced this, when we had a user who had filters that matched so many elements, and then we had to retrieve that kind of list. And with the old implementation, it was just retrieval of the filters before we did any vector search, and the latency was already too high. And now with the roaring bitmaps, that is super blazingly fast. Again, sort of one of those implementation details that you don't have to worry about, but you have to worry about your end-to-end latency. So the kind of effect is the benefit that you will get. Then there's also the ability to combine the semantic search with the traditional search. So if you have a case, and of course, there are tons of benefits of semantic search, but sometimes, so for example, when we go out of domain, could be that a semantic search would match or would not match on a rare, very specific keyword, which is exactly what keyword search is good at. So we saw that in the example where capital matched for capital punishment instead of capital. But if this was another rare word that had to be contained, then there are situations where you want the best of both worlds. And again, Weaviate here gives you this kind of end-to-end perspective where you can just do that in one solution. So you don't have to do, let's say, only your semantic search in Weaviate and then maybe run Elasticsearch on the side and do your keyword matching in Elasticsearch. And then now you have this kind of problem. You need to merge two sources and you need to maintain two things, and these probably scale differently, and there are probably different skill sets to operate them. So basically you have everything twice. But you don't have to do that, because you can do the hybrid search straight inside of Weaviate and use both a sort of lexical as well as a semantic index if you need it. There may also be cases where you don't even need it, because the semantic search is just good enough that you don't need those keyword matches. But if you do, then Weaviate has got you covered for it.
So yes, so it's certainly not as pretty as the demo from Etienne. But it's like same corpus. So here it's comparing lexical search with Elasticsearch and semantic search using Weaviate. But yeah, we build it independently. And yes, so for me, the API works. So if you search for how is the weather in Toronto, lexical search over-indexes on weather. So it thinks whether that's the most relevant term. Here, let's find all the articles talking about weather. And the first result is like studying how the weather works on other planets has been helpful in understanding how weather works on Earth. In a multilingual setting, the results is much better. So the top result here is from the Spanish Wikipedia. You get the information that Toronto has winters that are like really cold with maximum temperatures below -10. And then you find like information from different languages like English, German, and all, like even here down, I think that's Korean. So finds like from Korean Wikipedia information that Toronto has cold, humid climate. Also, as mentioned before, if you search for like capital France, again, lexical search totally over-index on the word France. So finds like the results France 24, Vichy France, Ile-de-France, and so on, but it's not finding the information about Paris. And again, you can filter on it. So for example, you not say, yeah, I want to search like all Wikipedias. I just want to search the Japanese Wikipedia because I like Japanese, and then you find the relevant information on the Japanese Wikipedia. Again, here with the help of Google Translate, we find like, okay, here we have the information, the capital is France. And you can also search like Arabic Wikipedia, and it's using it like what Etienne said in the background, these filters. So in the Weaviate database, we have the filter, what's the language? And then you're able to filter on this. And what's the filter? It doesn't matter. It can be the language, can be the quantity, it can be the popularity, it can be, is it available in stock or not? So a combination of these filtering and the semantic search is like really powerful to give you like an excellent search results. And what's really interesting about semantic search that it works across languages. So in many settings, you don't know in which language is the document you're looking for. So if you're working on a multinational enterprise, There's documentation available in many languages, and you just don't know like which team and which country did work on this. Is there some information? Or also in finance, you do like research on some product, on some company. Maybe there's like really, yeah, this needle in the haystack. So maybe some Chinese newspaper talked about this key information that will have like a massive impact on the supply chain of Tesla. But yeah, sadly, it was in Chinese. And because you didn't look for like Chinese content on this topic, you were not able to find it. But because it's like agnostic of the language, you're able to search for it. So you can just search for it and say, I don't know, impact on Tesla, and then find like some Chinese results talking about like Tesla. Okay. That's so much from my side on the demo. Did it work in the meantime again for you, Etienne?
Let me check again if it works now. Nope, unfortunately, still not. But we can follow up with this because we had planned a really cool demo to show the multimodal aspect of it, sorry, the multilingual aspect of it, how that works across multiple languages. So it's a bit unfortunate that we can't show that at the moment. But this will make for a nice 2-minute clip that we can share on Twitter tomorrow. So that'll be the silver lining of it. Nevertheless, let's maybe continue in our slides either way, because we also have something about deployment options that we wanted to talk about. So let me quickly continue sharing my screen. Okay, so for going to production, first one I think is from your side, Nils.
Great. So going to production, so at Cohere, we're following like a 2-stage approach. On the one side is the API. You get the API key, and we fully manage the models, and it's like pay per API call. So this is great for prototypes and demos. If you have like 100 calls, 1,000 calls, it's like pennies you're paying. So it's like really nice for prototyping. You don't have to manage like any infrastructure. And so within short time, you're able to have like really solution that's up and running. However, in many settings, if you want to go to like production setting, I think API is not the best solution. So because you don't own the model, you don't control the model. Data privacy is always a challenge, especially for European customers. So we also provide options to do like on-prem deployment. So on AWS, that's the first version we have. It's like really easy. You go to the marketplace, you check it out, and then you can spin up like an instance in your AWS account. It's in your AWS account, so no data is leaving your cloud. Pay per use per hour. So if you need like 1 hour, you pay like $5 for it. And this is like also really great for production settings. So if you have like millions of search queries and you have like really successful product, it's much better if you own the model and can deploy it in yourself. And yeah, for Weaviate, it's really similar. So if you want to go to the next slide, Etienne, and take over.
Yes. So this is almost an exact copy of the previous slide, just replaced Cohere with Weaviate. So for Weaviate, we have a total of 4 deployment options, which is a bit of a lie. I think the last one isn't really a deployment option, but we'll get to that in a second. But here, very similar. So if you want the fully managed experience where you basically get the pure SaaS kind of experience, it's fully managed from our engineers. It's pay per use. So pay per use for us means vectors stored and vectors queried. So if you have an empty Weaviate cluster that runs forever, you pay nothing. If you have some data imported or some vectors imported, then you pay something for the storage, and then you pay per query. So it really, the payment model basically is tailored to your usage of it. As of today, or as of yesterday, actually, this is in public beta for GCP. We're planning to add AWS and Azure as well, but that's not live yet, so that's why it's grayed out here, but that's on the roadmap. And within GCP at the moment, you can choose your region freely, so you can deploy this close to your workloads or to your customers. Supports high availability, supports multiple SLA levels. So if you want support or different kind of support contracts, you can have that as well. And then on the other side, we have, similar to what Nils just shared about Cohere, you can also deploy Weaviate in your cloud environment. So we call this hybrid SaaS. And the idea is that you get the SaaS kind of experience where everything is managed for you, but still it runs in your cloud. And why would you want to do this? As Nils just said, so for privacy reasons, this is great because your data never has to leave your environment anymore. So you could have your Cohere embedding model and your Weaviate database deployed in the exact same environment together with the rest of your application, and then the data just always stays there. And of course, it also gives you benefits like network locality. So you don't have to send queries across the world or send queries across data centers or even across cloud providers that can already add like 100 to 200 milliseconds latency. You get to avoid all of this, but still it's managed by Weaviate. So Weaviate engineers make sure that this stays up, make sure that this stays scalable, make sure that basically everything is running for you. And again, here you can have multiple SLA levels to pick what kind of support or other objectives you need. And of course, there's the option to fully customize this. But then, because Weaviate is open source, if you say, well, I don't want to sign a contract yet, or don't want to go into any kind of commercial offering yet, you can also you could either try it out for free, or you could completely self-host it if you want. So you could run a Weaviate on Kubernetes, for example. It's not a requirement, but Kubernetes is very common to use. We have a supported Helm chart. And then it's your own responsibility. It's completely free. There's an open source license, and there's some limited support. So basically community support on a best effort basis. And very new, so we just released this today, I believe, is Weaviate Embedded. So Weaviate Embedded is not, and that's why I said like it's a bit of a lie that this is a deployment option, because I guess it doesn't deploy it anywhere. But Weaviate Embedded is the idea that if you just want to get started, or maybe if you're using Weaviate in combination with model training, where your environment is either a Python application or a Python notebook, then you can now use Weaviate Embedded, which just runs Weaviate in the background, basically. So you run it, completely control it with the Python client. The API is exactly the same. So this was very important for us, that we make this like that you're not stuck in embedded mode and you can never get out of it. If at some point you say like, okay, I've outgrown my embedded space and I would like to move to production, and now you have like breaking changes in the API or something. No, it's the exact same API. And you can easily migrate basically this into either a self-hosted or a managed environment. And yeah, get started in a sort of, it makes the barrier to entry, or it lowers the barrier to entry even further, because now you can get started with Weaviate straight from a Cohere notebook, from a Python notebook in combination with the Cohere client and the Cohere module. Cool. So that is it from our side. Conclusion: semantic search is amazing. Live demos are a bit of a risk, but Nils had an awesome backup. So thank you very much for jumping in with that backup.